Okay, so welcome everyone to our webinar this morning. My name is Jen Hicks and I'm the Associate Director of the NCSRR at Stanford University. I'm joined by Ayman Habib, who's the lead OpenSim application architect at Stanford, along with AJ Seth, who's the lead OpenSim API architect, also at Stanford, and then Tom Uchida, who's also a key member of the OpenSim development team, is joining us as well. He was a research associate at Stanford, and he's recently started as an assistant professor at the University of Ottawa. We're excited to join you all this morning to tell you about our new major release of the OpenSim software. OpenSim, if you're new to the software, is free and open source platform to model the musculoskeletal system and simulate how humans and animals move. The software is being used, for example, to explore how injury, surgery, assistive devices, and many other factors affect human movement. In our talk today, we'll tell you about the new version of the OpenSim software, version 4.0, and also do a live demo. We're excited to share a variety of new features that are driven by the needs of the biomechanics and rehabilitation research communities. And this research community is diverse. So this slide will show a few exciting examples of how OpenSim is being used. So Ravi Balasubramanian of Oregon State University is using the software to model the effects of artificial tendon networks and simulate how they affect hand motion after a tendon transfer. Marjolein van der Kroot from the VU in Amsterdam is using OpenSim to simulate the effects of muscle spasticity. Stefan Verbruggen and colleagues at Imperial College in London are using the software to simulate fetal kicks in the womb. And Brian Umberger and Frank Supp at UMass Amherst and the University of Michigan are using OpenSim to model the limb socket interface in amputees. So our users are really pushing the software to new and exciting use cases, which necessitates a set of flexible tools for studying movement. And this is what drove our development of 4.0. So here's the plan for our presentation this morning. We will briefly tell you what is OpenSim, so provide a quick overview in case there are any folks joining us this morning who are new to the software. And then we will tell you what's new in the latest version of the software, including a live demo. And we'll wrap up by telling you how you can learn more and get started with the new software. So first, what is OpenSim? So OpenSim is free and open source software for modeling humans and animals and simulating their movement. So OpenSim can model many structures, including biological and mechanical systems. So there are components and tools to emulate neural control. There are components to model biological joints. So humans are not composed, for example, of all pin joints. Models can be tuned and scaled to individual subjects. And we provide sensors to estimate metabolic energy consumption during movement, muscle tendon dynamics, and models of ligaments and joint contact. And OpenSim can also model non-biological structures like assistive devices and prosthetics. We've designed OpenSim to be flexible and modular so that others can extend and adapt the software to their own research needs. So models can be as simple or as complex as you need. Just combine the elements that you want. For example, on the left is a simple hopper with a block and 2 links. On the right is a model with 23 degrees of freedom and 92 muscles. And you can query the model or any of its components to understand and compute anything you'd like to learn from a simulation. For example, one type of what we call a component in OpenSim are the muscles. From a muscle component, you can output things like fiber length, fiber power, force multipliers, and many other quantities during a simulation. Joints are another example of a component in OpenSim. So from joints, you can output their joint reaction forces. So you can just ask a joint what are the reaction forces in the joint. These are just a couple more examples of components and outputs from components, and we'll learn a little bit more about this in the demo. So OpenSim also provides a user-friendly GUI or graphical user interface that allows easy access to this underlying functionality. This GUI is now cross-platform in OpenSim 4.0, running on both Mac and Windows. In the GUI, you can load and visualize models. There's also a suite of tools for importing experimental motion capture data, computing inverse kinematics, inverse dynamics, and generating muscle-driven simulations. And we'll see a little bit more about this in the demo. You can also develop and share models with OpenSim. So if you've done it before, you know that creating a new model is a ton of work. So OpenSim also provides a repository of models so you don't have to reinvent the wheel when you're starting a new study. So there's an online repository of model. A couple examples are shown on this slide, both from our labs and other labs around the world. For example, Matt Demir's and colleagues created a model with a physiologically accurate model of the ankle and stretch reflex controllers to understand the role of reflexes in preventing ankle inversion injuries. Kat Steele and others have created models to simulate a crouch gait pattern in children with cerebral palsy. AJ Seth and Ricardo Matias and colleagues created a model of the shoulder with physiological scapulothoracic joint that's fast and accurate compared to bone pin data. And you can also create animal models in OpenSim. So this is an ostrich developed by Jeff Rankin and colleagues as the final example I'll show on this slide. So OpenSim is a software package, but we also want it to be a community, and this community is growing and diversifying. So the OpenSim community has thousands of users and hundreds of experts around the world. This map shows visits to our documentation, for example, over the last year, so it really shows the worldwide impact. As I mentioned earlier, the community is diversifying. So this bar graph shows publications citing the OpenSim software organized by research category, where each bar shows the % of publications that come from a given discipline. So we see OpenSim is used for biomechanics research and is also used in robotics, computer science, and the neurosciences. So OpenSim is enabling interdisciplinary collaboration between biomechanists and all these other fields. And then this plot shows the cumulative number of unique users of OpenSim since its release in 2007. And I think as of this morning, we're up to nearly 39,000 individuals who have downloaded the software. And we're honored that many of you are users from the community are joining us this morning to learn more about the software. And so we've been hard at work on creating the next version of OpenSim in response to feedback from our community. And so I'll summarize the improvements we've been working on, and then we'll start the live demo. So planning a new software release is challenging. And to help navigate this challenge, we talk to our users. So we collect feedback from users through surveys. Thank you to anyone who's filled out one of our user surveys. We also talk to folks at conferences, workshops, and see what questions are being asked on our user forum. And this feedback drove our development plan. So first, OpenSim users, including me, use Macs. So the OpenSim GUI now runs natively on both Mac and Windows. Also, researchers, teachers, and clinicians need to make compelling visuals to share their work with others, whether it's other scientists or a general audience, students in a high school class. Researchers also need fast and flexible visualizations to help them build and troubleshoot models and simulations. So we've also upgraded the visualizer in the GUI to generate beautiful and modern visuals. Another frustration we encountered was the difficulty of getting data into and out of OpenSim. Getting your data into OpenSim can be a big startup cost, and we want to lower the barrier for new users to get started. We also want users to be able to get anything that's computed about a model or simulation easily out of the software. So before there was frustration that I know OpenSim is computing this, but I can't get it out. And so we want to solve that frustration as well. So we've added better support for C3D files and new output tools to simplify the process of getting data out of a simulation. So this will help our users like you continue to push the bounds of what's possible with computer simulation. And fourth, Matlab and Python scripting are huge. So many of you are already using this scripting functionality, but we heard that users want to break out of the standard workflows and design their own studies. Matlab can enable this. You don't need to learn C++ programming to customize and extend OpenSim workflows. And so in the new version of the software, we've also made a host of improvements to the API to benefit scripting users as well as developers. Okay, so let's jump into OpenSim 4.0. Just one more slide before we do that. So to tell you what's coming, first we will generate and analyze a muscle-driven simulation of a vertical jump with a counter movement. So we'll be using a simplified model of the musculoskeletal system with 18 muscles and 10 degrees of freedom. So Ayman and I will together demo the new visualizer and the new capabilities for analyzing simulation results, so using those new outputs. And then AJ will show how we can use new components and API features to build, edit, and analyze a simple model in the GUI. So with that, I will bring up OpenSim, and Ayman will start our demo. All right.
Thank you, Jen. So when you launch the application and load the model, it will look similar to what you see here, a jumper model, and you will immediately notice the brand new visualizer. We're also running on a Mac, so that might not be clear from the slides. But for new users joining us today for the first time, I'll do a quick tour of the application or GUI, and then we'll jump into the example that we want to demonstrate. The fundamental job of the application is to allow users to inspect models and to perform studies to analyze these models. There are multiple ways to do this, and the different parts of the application allow you to do this inspection. First is the navigator window, which has a hierarchical representation grouping the components that make up the model based on type. So you'll see we have ground, we have list of bodies, and if you scroll, you will see that we also can expand the list of joints and inspect each one of them. And associated with that, I will go back and expand bodies. If you click on one of these bodies in the navigator, you will see the bottom window here, the properties window, has the attributes of this body that you can basically modify in the model file. What's new here is there is a new tab called Outputs, which describes the list of quantities that are available through this component in OpenSim 4.0. So for example, for a body like pelvis, you can get the transform, velocity, position, and various other quantities. Now, another kind of pane that you can use to explore the model is the coordinates pane, which allows you to inspect the degrees of freedom in the model so we can pose the model the way we want. So I'll go here and expand the hip flexion, for example. As you move it, you will see that visually the hip is flexed back and forth, and usually the ranges specify how what are the valid ranges for this coordinate. To quickly see the bodies and joints in the model, you can't tell that immediately from this view. So we have a different view specifically for that, which is the topology view. So if you go here and pick the topology view, then you will see a tree structure that contains the bodies and the joints connecting them. For example, I can immediately tell from this graph that the hips are joint connects the pelvis body and femur body, and you can extend that to all the other bodies and joints in the model to see how they are connected. I'll close this now and we'll go back to the last view, which is 3D visualizer, and this is the view that undertook the most changes and upgrades, as Jen pointed out, to make the visualization more appealing. You will notice that the bones appear more realistic than they used to in the previous versions. They are not as shiny, and that there is a floor and there is shadow on the floor. And this could be helpful in the case when you want to create beautiful images for a figure or presentation. And we'll go through some steps here to demonstrate these functions. But first, let me highlight some muscles, for example, that if you are interested in these muscles, you can change their colors. This has been added in version 4.0, so I can select these muscles and give them a different color. Now, if you want to customize the scene where the model is situated, then we can make him go to town by changing the picture. So instead of blank background, we can change that to something like a city where you'll see high-rise buildings and a more interesting background. Of course, the floor now doesn't match, so you can change that as well to some sort of a brick. And this looks more like a city, I guess. And you can also customize how the shadow is cast, because the shadow is a side effect of the lighting. So if I zoom out here and click on this scene lighting, I get a triad attached to the light source. By moving this around, I can position the shadow wherever I want, so it is behind the model or on one side rather than underneath the model. So assuming that this is the really picture that I want to take, then I can go here to the slider for snapshot quality, which allows us to get high resolution images, and then just slide it up. And then when I click on this camera, I get a screenshot. You can easily navigate the view in 4.0 much easier than we've done in the past. So that will allow me to zoom in on a specific set of muscles and take another snapshot if I want to. And finally, I will return everything to the standard background, I guess, for the rest of the demo. So I'll just stick with black background and wood floor. And now we are good to go with our investigation and try to load some experimental and simulation data to explore the jump. So now I will turn it back to Jen.
Awesome, thank you, Ayman. So I guess one caveat, you're going to have to download the software and try it yourself to really see these new visualizations, because we're losing a little bit in the translation to WebEx. So we hope you will all try out the software yourself to really see the new visualization. So as Ayman mentioned, now let's load some experimental and simulation data to explore the vertical jump. So one thing I mentioned in the slide deck was that we now provide support for C3D data. We don't have time to get into the whole process, so just as a quick proof of concept, I'll show you, I'll plot some of the C3D data directly. So for the demo here, we're going to generate a muscle-driven simulation based on experimental data for a jump. And so part of that experimental data will be ground reaction forces. So I'll bring in I'll load the file with the C3D data for the jump and plot it directly here in OpenSim. So I'll choose the X, Y, and Z components of the ground reaction force. I'll plot that as a function of time, add it to the plot, and there we go. That's pulled directly from the C3D file. We see the X, Y, and Z components. We see that in green, the Z, that's the vertical force. So we see the counter movement of the jump, the flight phase, and then the landing. And so today we'll just be focusing on the counter movement and the flight phase of the jump. So we'll have a future webinar where we teach you a little bit more about the new C3D functionality. So now let's move on to muscle-driven simulation. So I have marker data that I've already used to scale the model, computed inverse kinematics to find the joint angles that best match the marker data. We've reduced residuals to get good agreement between the ground reaction forces and the model. and the motion, and then I've used computed muscle control to generate that muscle-driven simulation of movement. And in the interest of time, since a lot of that process is pretty similar to previous versions, I'll just go ahead and load the results. So I'm going to load the results of CMC. So here's the results from CMC, and I need the states file, which has all the joint trajectories and the muscle activations. So now we see the model is posed. I think I'll need to zoom out just a little bit so we can see the full jump. You'll see that the muscles now match the activations, and we also have a nice new color scheme for muscles. And I'll slow it down a little bit so we can really see what's going on. And here you can see, oh, I didn't zoom out enough. Here is our jump. Okay, so Ayman showed you how we can make nice images. You can also make movies in both Mac and the Windows version. To do that, I'll go ahead and start my jump. And oh. Okay. There we go. Okay, here we go. Sorry if it's showing up as jerky via the WebEx. Again, you'll have to try it for yourself. But we'll go ahead and record a couple jumps. I'll save that to the desktop so we can find it easily. Go ahead and stop the jump, and then we can open up the movie right in your browser. So there's my nice movie of the jump. Play that one more time. And so you could upload that to YouTube, add it to a presentation, easily share it with others. So now let's get back to learning some more about what's happening in the jump. And to do that, we'll use those outputs that we've been talking about. So Ayman showed the outputs a little bit. I am interested in learning a little bit more about how high the person jumped. So I can look at the outputs of the model itself, and I see that I can look at the center of mass position. So that sounds like a useful output. Another output I'm interested in is how high the hand is reaching. So if I navigate to the right hand in the set of bodies, I see acceleration, and there is position. So I can also use outputs to ask the model what about the position of the hand. And then the other thing I'm interested in is the role of the plantar flexor muscles, and in particular what their force generating capacity is during the jump. So if I look at my muscles and choose the soleus muscle, for example, I see lots of outputs, and the list, as you can see, goes down pretty far. So there's lots of things you can query a muscle to learn. But I'm interested in the active force length multiplier. And so that's the other output that I'm interested in. And if you look down here in the bottom of the output pane, you'll see what looks kind of like a path on your file system. And this is just the now all the components and the outputs in OpenSim each have a unique path. So you can specify exactly what you want. And so the path for this output, for example, tells me I'm looking at part of the force set. So muscles are part of the force set in the model. The particular muscle is the right soleus. And this vertical bar tells me it's an output of the soleus, and in particular, the active force length multiplier. So these outputs you can use in scripting. And we've also added an interface in the GUI so that if you don't want to, or you're not familiar with scripting, you can also just do it directly in the GUI. So to get to those outputs, I'll launch the Analyze tool. And I've pre-specified a setup file just so I don't make any mistakes during the live demo, but I'll walk through and show you how it's set up. So in the Analyze tool, so I'm analyzing doing a post hoc analysis of the results of CMC to get these new quantities from the simulation that I didn't compute the first time around. So I specify the states from CMC here. So that's the motion that I previewed earlier, if you remember. Here's the time range. So I'm looking at the counter movement to the just before landing. And I will save the results in a folder so I can find them easily. I want to give it the same setup, the same set of files I used to run CMC. So I have the same actuator file, the same external load specification. And then what's really new is this output reporter. So I can tell OpenSim exactly the outputs that I want. Previously, you couldn't get all of these things out with an analysis that I'm going to show you. Or if you could get them out, you get a bunch of Excel files that you'd have to wade through, and it would be maybe compute things you didn't want or you didn't know what Excel file to look at. Now we're going to specify only and exactly what we want. So again, I've already typed all this in so I don't make any errors in the live demo, but we'll see the center of mass position for the model, the position of the right hand, and then I'm going to output both the active force length multiplier for the Soleus and the gastroc. Okay, so I think I have everything set up. I'll go ahead and hit run. I will do this part live. And again, we're still analyzing that jump. There's my nice jump motion. And so let's go ahead and look at those results. So I'll bring up my plotter again. And again, the first thing I was interested in is the height of the jump, how much the center of mass is displacing, and how high the hand is getting. So if you remember, I saved my results in the planar flexor outputs folder. So I'll go ahead and open that up. I get two different files. One contains all of the things that were 3D vectors, so the positions will have X, Y, and Z components. And then I just have some scalar values as well that will be in the second file. The positions are in the one with 3D vectors. I happen to know that in my OpenSim coordinate system, the vertical is Y. So I'll get the Y component for the center of mass position and the Y component for the hand's position. Again, I'll plot those as a function of time, add them to my plot. And here I see in blue the hand. So the hand reaches about 2.5 meters. And then my center of mass is displacing over half a meter. So not a bad jump. Kudos to our test subject, who may or may not have been a grad student in the lab. So that's my analysis of the position. And again, you could do some of this previously, but you get a bunch of Excel files and you couldn't directly query what you want. We can also get some brand new things like the force multipliers. Those were not easy to get out previously. But now I can just, again, load the file. It's in this one with the scalar results. And there I see the active force length multiplier, so the force generating capacity as a function of the length of the muscle for both Soleus and gastroc. I'll go ahead and add both of those to my plot as a function of time. And let's see. So, so kind of interesting here. So for the gastroc, since during the counter movement the knee is flexing and the ankle's dorsiflexing, it actually stays near optimal throughout the counter movement. The Soleus, since just the ankle's dorsiflexing, seems like it's getting longer, losing its force generating capacity until right before push-off when we need the Soleus, it actually is near optimal as well. And then we lose force generating capacity during the flight phase, but we're just in the air, so not as big of a deal there. So that was a very quick demo of how you can use these new outputs and the new visualizer in OpenSim 4.0. And with that, we'll go ahead and wrap up the jumper portion of the demo, and I'll pass it over to AJ, who will teach you some more about some of the new other new components in OpenSim and some of the new API functionality.
Thank you, Jen. Well, hi, everyone. Thanks for joining us this morning. I'm pretty excited to talk to you today about the API changes that will enable us to do some customized model building. Thank you. Oh, let me fast forward through here. Okay. So the plan for the model building demo, I wanted to demonstrate how easy it is, kind of a bit of a teaser on how to build a model from scratch in OpenSim using components that we'll add to a model. Some of those new components consist of frames, so I'll talk to you what is a frame and how do we use it. And then we'll use the scripting environment in the GUI to build the pendulum. And then I'll show you how we can access those outputs live to look at results in the GUI. So first of all, what's a frame? So frame's a new notion, well, not a new one, but a notion now in OpenSim that we've formalized, and it represents a reference frame. It's just frame is short for reference frame. So it's 3 orthogonal axes that define a location and orientation with respect to another frame. So of course we need one other frame, and that's always going to be ground, and it's always going to report 0, 0, 0 for its location, and its orientation is always identity. And then we can express any other vector in any frame. So let me give you some concrete examples, right? So frames represent these physical spatial locations, like ground, as I mentioned. It can represent the center of mass of a body. And it can also represent fixtures, where we're going to connect joints and forces to the body. So now that we know how to use frames, we're going to apply them to build a pendulum in the GUI. So, but before we do that, let me just describe what the commands are, and so that you know exactly what we're going to be doing in the GUI. The first thing we're going to do is we're going to create a bare model. So we'll just call the scripting environment to give us a model. That's the first line here. We're going to set its name, and then we're going to get an access to the ground. So we have ground, we have basically nothing happening, just a ground. But now we're going to connect things to the ground. We're going to create a rod with a dimension of 1 meter in length and a radius of 2.5 centimeters. And now we're going to actually add a body to the model. So we're going to add the rod to the model, and we're just going to call it rod. And this convenience utility method is just going to add a body with some default mass and inertial properties that we can now use in the GUI and the property editor in the GUI to change their values. And we will want to see the rod, so we're going to also attach some geometry. In 4.0, we have built-in geometry like cylinders and spheres and cubes, and they take just their dimensions to get them to appear. So this one's going to have the radius that we defined, and it's going to have the length that we defined. And boop, we'll see the rod appear in the GUI. But the rod itself isn't going to move because it's not connected to anything. So we have to first define how we want to add the rod to ground. And the first thing we need to do is define some of the frames that we want to connect to, as I described before. So we're going to add an offset frame. We're going to call that the parent in ground, P. And we're going to put it the length of the rod above ground. And we're going to create a child frame, and we're going to connect it to the rod, and then it's going to pivot about where that location in the rod is. So C is for the child frame in the rod. We still haven't added the joint, so now we're going to do that. And how do we do that? We're going to say we're going to connect the body, this rod body, with a joint. So we have to tell it the model we want to add the joint to, the 2 frames we're going to connect together, We're just going to call it pin and the type of the joint. So we have slider joints, ball joint, universal joint, and in this case, we're going to use the pin joint. And what the pin joint is going to do is going to align the two axes together, once we have them together, and so that they pivot about the common z-axis, which is pointing out of the floor. For that to happen, though, we've just described what are the components in the model. We actually haven't built the mathematical system of it. So the next thing we need to do is call a knit system, which is going to bolt the model at the pin as we requested, and give us our initial state. If we haven't specified any initial joint angles, then it's going to just be 0, 0. That's why it's vertical and aligned in the ground. And then the next and last thing we're going to do is load the model in the GUI, where we'll be able to visualize it and animate and simulate and animate the model. So let's go ahead and switch and do that in OpenSim. So we're going to switch into the scripting shell here. And I'm going to run the first set of commands. First, I'm going to run the utility methods that had like add body to model and connect body with joint. So those are in the model building functions. This is going to be in your distribution. And then I'll run it. Actually, we don't need to look at it. So I've just run those scripts. It has those methods inside. And then we're going to run the creation of the rod. This is going to create and add the rod to the model. Okay, so there we've created, those are our dimensions, 1 meter length, 2.5 centimeters. And now we have added the rod to the model. So just to prove that it's there, I'll say, hey, Rod. Okay, yeah, your name is Rod. And then I'll say, Rod, what's your mass? And it just got a default of 1 kilogram. So now we have a rod, but we haven't connected it to the model yet. I mean, connected it with the joint yet, so it has no motion. So we're going to now connect it to ground so connect the rod to ground with a pin joint. And those are the last set of commands that I showed in the GUI, in the slides. Okay, so now that we have the pendulum, and we also ran load model, so it already popped up in the GUI here, so we can actually look at the pendulum. Do you notice anything wrong with it? It's rotating about a frame, which is going to be, we can look at these frames. So if we go to the body and we go to the rod, we can show its origin. And I can also show where in ground I want it to rotate. So those are the two axes that it's rotating about. But I want the axis of rotation to actually be up here. So we can go to the definition of the child joint, of the child frame, which we defined in the rod. This previous rod offset just has the cylinder geometry that's connected to it. But this is actually the joint frame. So this one I want to change. So I'll go back to the properties view. And there I see the translation. And I want this translation to be at the top of the 1 meter rod. So from the center, we're going to go 0.5 meter. There we see it update live. It's now swinging from the, sorry, just got a little fast. I'll simulate it so that it's a little bit nicer looking. So we can simulate for just say, oh, just before I do that, just to show that this is real, I'm going to change something about the model in the GUI. So I'm going to show that we can change other properties. We change its location, but we can also change, for example, the mass. So let's make the mass like 2.345, something like that. So now we've changed the mass of the model as well. And now we're going to simulate it. 10 times, let's not simulate forever. 5 seconds is more than enough. And then we're going to simulate it. Press the running guy. So the simulation already ran. It was too fast to animate, but we can see it in the replay. And I'm actually going to slow it down so it doesn't look too jerky on your replay on WebEx. There, we built the model. We've played it. We've visualized it in the GUI and then even ran a forward simulation on it. So now let's go back to the scripting environment and let's probe this model. Let's get access to some of the outputs. So let's get the current model because we edit it in the GUI. Let's get the current state of this model. And let's also get access to the individual rod. So we know that's in the body set. We added a body, and we're going to get it by name. We just called it rod. It's a good thing that it's a short name because I cannot type. And then we can say, rod, give me your mass. So we can see that this is the changed model. So we've changed the model, we have access to it. And now we can say, well, Rod, what are your outputs? By doing print output info. If you don't like to type, you could go into the outputs and look at the Rod outputs here. You can see angular velocity, but if you're a scripter and you want to see, you can go Rod print output info. Go to the messages window, and you can see the same list. So from the scripting environment, if you're not in the GUI or you're in Matlab and you want to see what are the outputs of any component, you can just ask for the output info. So now once you actually get the angular velocity, say, omega, so I'm going to ask the rod for its output by name. Angular velocity. And now I have access to the output. Now I can ask the output for its value. And because it's a 3D vector, I'm going to ask it as a string, so it's already formatted to be visible in the scripting shell. Not sure what happened there. Okay. So now if we go to the beginning, of the simulation, we should see that the simulation result, what's going on? So the simulation result should be very slow. So it's barely moving here. It's just 0.3 radians per second. Somewhere at the bottom, it should be a lot quicker. This is just to show you that this is live results from the state that we're playing back. And then if we continue on, it should be close to 0 again, 0.6 radians per second. So this is just a quick teaser on building a model in the GUI and accessing outputs live. And you could use that in your own functions and batch processing. So that's it for me. And I'll turn it back over to Jen.
Great, thank you, AJ. So this is, the demo is a quick teaser. We plan to have some future videos and webinars to show off more functionality, and we welcome your feedback on what you'd like to hear more about. But to wrap up for today, I want to show you how you can get the software and how you can learn more about how to upgrade if you've been using previous versions, and how you can learn more about using the new features. So you can download the software from our website on simtk.org. You'll find both a Windows and a Mac installer. We've strived to make the upgrade process as seamless as possible, and I'll show you where you can find the full set of upgrade notes. But a couple key pointers about upgrading are on this slide. So editing your models in the GUI and via scripting is generally going to be easier and less error prone. And so you'll notice that the format of the XML has changed. So again, we encourage you to use the GUI editing and scripting. You can open your 3.3 models in OpenSim 4.0, but just a reminder that once you edit and save a model in 4.0, you won't be able to open it back up again in 3.3. So if you're going between versions, save a copy if you want to use your 4.0, if you want to use a model again in an older version. And then we've also upgraded how custom joints are defined to make them less error prone. If you have custom joints, especially with coupled motions, make sure you review the upgrade notes, and you'll also see a pop-up menu in the GUI when you load a relevant model that has a coupled custom joint. So in our documentation, you can, so we'll follow up with a link to this, but if you go to the section What's New in OpenSim 4.0, that'll include a more detailed description of new features and links to relevant documentation, along with a link to the upgrade notes. And again, we'll follow up with direct links to all the things I'm talking about. We've also upgraded our user guide and our examples so you can see how to use the new software as well. And as always, we encourage you to use the forum as well to ask us additional questions. If you want to learn more about the software, you can also check out our recent publication in PLOS Computational Biology. We'll email a link after the webinar, and again, we'll send you those download links and links to our documentation for 4.0. So in closing, before we get to your questions, I want to acknowledge the huge team of contributors that has made OpenSim 4.0 possible. So some of the key contributors are shown on this slide. In addition to Tom, Ayman, and AJ, who are tuned into the webinar today, Chris Dendia, Carmichael Ong, James Dunn, and Nick Bianco have also been vital in pushing OpenSim 4.0 over the finish line. So thank you to them, and also thank you to all of you who gave us feedback and helped with beta testing. This has been a true team and community effort. OpenSim has also been supported by a wide range of grants, a big portion coming from the National Institutes of Health, which funds our National Center for Simulation and Rehab Research. And with that, we'll go ahead and take your questions. To ask questions, you want to click on the Q&A panel. Make sure you choose to ask all panelists. So we'll go ahead and take questions. And then I'm also going to, Tom, can you hear us, or can you test your audio real quick as well?
Yes, hi everyone.
Good, okay. Oops, so we can hear Tom as well. Yeah, so let's go ahead and get to our questions. Again, put those in the Q&A panel. And then AJ, and Ayman, if you can scoot up closer so we can see you. There we go. We're trying to get to our questions here. Okay. All right. Okay, I might just bring my computer up. Sorry for the delay here. We're not trying to dodge your questions, I promise. Okay, here we go. Now we're in business. All right. All right. Okay, so here we go. Okay, so one question, this is from Naji Alabeji. Again, apologies if I've mispronounced that. Do you have any recommendations on methods to convert sim models to OpenSim 4.0? Ayman, do you want to touch on this one?
Yes, I think the best way to do that is to import the model into OpenSim 3.3, save it, and then utilize the backward compatibility features of OpenSim 4.0 to get the model into 4.0.
Great, thanks, Ayman. Okay, so next a question from Hoon Kim. Says, thank you for the presentation. Could you show the process of converting or using C3D files into OpenSim 4.0? And that's a great question, and that's definitely something we want to show. But as you can see, just the things we took about 45 minutes to show. So we're going to show more details in a future webinar. And if you have some questions in the meantime, we also encourage you to ask questions on our forum. And there's a little bit of documentation as well in the user guide. So we're happy to help point you to that as well. Okay, so now a question from Arash Ganabadi. So I was wondering, how can we remove a muscle in the GUI?
Oh, this is not supported in the GUI right now, and so you'll have to remove it from the model file manually, basically. You can disable the muscles, but if you want to remove it completely, then it has to be done outside the GUI.
So you could do it by editing the XML file, and if you're working with the model and scripting, in Matlab scripting, you could do it there as well, right, AJ?
You could. Yeah, you have to remove it from the actual set that it belongs to, so from the force set.
Mm-hmm. Okay. So a question from Aram Munoz. Tom, if you're game, I'm gonna call you out to answer this one. So his question: dynamics in OpenSim are computed by a Newton-Euler algorithm, correct?
Yes, it's a recursive order N formulation. There are more details about that in some publications that I could potentially point you to.
Okay, we couldn't hear you, Tom, but Joy's giving us the thumbs up. I turned my speaker on, so next time we can hear you. Thanks, Tom.
I'm not sure if Tom referred to, there's a paper from 2010 about how we do the rigid body formulation, and particularly for the mobilized bodies. So if you want to take a look at that, that's more specific on how we formulate the equations of motion.
Okay. So next, a question from Felix Chenier. Again, apologies for any mispronunciations. So the question here: can you create objects other than by scripting? Do you want to answer that one, AJ?
Currently, no. The only way is through scripting, but you could do it in Python, Matlab, or in the GUI environment.
Yeah, so the approach that we took is that, so doing model building in the GUI is something we definitely want to achieve in the future. But to get there, the first step is to create the building blocks in the OpenSim API, which AJ kind of showed you through the scripting, to then build a GUI or a graphical user interface for then doing model building there. So hopefully coming in the future. So a question from Jonathan Mortensen. Will I be able to run all my 3.3 Matlab scripts without modification in 4.0? Do you want to answer that one, AJ?
Unfortunately, not all. The vast majority should. We did change the interface in some cases, and those are in the change log. So if you post a question on the forum, we can point you to it, or you can search on GitHub for the change log for OpenSim core. And you'll see what changes have been made, and they might not impact it depends on what you do in your script. Mm-hmm. You might not be impacted at all, but odds are that you probably have 1 or 2 columns that you have to update.
Mm-hmm. And then we have also updated all the example Matlab scripts that we provide, so you can look at those examples for how some things have changed as well. So now a question from Robert Huffman. Is the corresponding code body for OpenSim and SimBody available as it was for OpenSim 3.3? So the OpenSim source code is still open source as it was in previous versions, and actually the OpenSim GUI is now officially open source as well. Although we don't encourage you to try to build the GUI from source. You hopefully use the distributions we provide. We have in the past provided a zip file with the source, so you don't have to go to GitHub, you can just download it directly. I don't think we've put that up on SimTK yet, but we'll post that soon. Is that good? Okay. So a question from Luciano Menegaldo. So does the 4.0 version allow more flexibility to choose the static optimization cost function? So in the GUI, no. But actually with some of the new outputs and API improvements, it's actually if you wanted to write your own static optimization, say in Matlab, that's a lot easier to do. Granted, he's one of the grad students here at OpenSim, but he told me the other day that he was bored over the weekend and rewrote static optimization. So, you know, it's definitely has gotten a lot easier to do with some of the API upgrades.
And you can really leverage the optimizers in Matlab, for example. So you can basically write your cost function using the outputs from OpenSim and then use the optimizer in Matlab.
Okay, so another question from Arash Ganabadi. In MATLAB scripting, how can we visualize the model during IK?
You can. You have to turn the visualizer on. So the model has an option to turn the visualizer to have an accompanying visualizer, and that by default is false. So if you call that, and then you create the underlying system, you'll get a visualizer window pop up. That will be not the GUI's visualizer, it will be the OpenGL SimBody visualizer. But you can still see the model. You just can't interact with it.
Okay, thanks, AJ. Another question from Daniel Iordanov. How can we adapt C3D marker positions to a TRC file in OpenSim? Well, so again, we'll get into more details in a future webinar, but AJ, if you want to answer briefly.
We're currently working on scripts that might be already available to do that for you, so to read the C3D using OpenSim's file reading capabilities and then convert it to a TRC. The long-term view is that you won't need to do that, that we'll be able to use C3Ds, but that's not in this current version.
Okay. So next, a question from Luca Modenese. Hi, Luca. Is there a plan of having a Linux version of OpenSim as well? Ayman, you want to take that one?
Yes, we have many contributors who have built OpenSim locally on Linux. There was just not enough demand to support and build on our side, but if somebody wants to take this over and start a build, we'll be happy to help them streamline the process.
Are you willing to do that, Luca? Yeah, if anyone is interested in Luca or anyone else, let us know. So a question from Wellington Pinheiro. Is there any new functionality to give more access to ODEs, which drives models, and through that help controller design?
Well, you can access all the derivatives that are being integrated. So yes, and then there are some-body methods to get, for example, the partial derivative of a location with respect to the joint angles. The complete derivative of the kinematics with respect to your controls, that's a little bit more tricky. So it depends on what level you want to go to.
Okay. Great. So Tom, if you're still online, and I have our speaker turned on so we can hear you as well in the room. So a question I'll send to you. To calculate the metabolic cost from the Umberger method, do we need to calculate an MVC first, or is that something you don't need?
Well, the metabolic calculation is a function of the maximum isometric force of the muscle, but that will be a property that's already a property of the OpenSim muscles. So that's not something extra you need to specify in the metabolic calculator.
Okay, awesome. Thanks, Tom. And we heard you that time. Okay. So a question from Adam C. Has OpenSim 4.0 improved on file management and the amount of setup files for each of the processing steps as compared to the previous version? I think this answer is yes and no. You know, part of the issue that was hard before was getting the information out of the simulation that you want, and so you'd have to run a kinematics analysis and a muscle analysis, and it would generate many Excel files. So we've cut down on the number of files that are getting generated there. The setup files that you give to a tool, that process is largely the same. But again, you know, we appreciate your feedback that's something that is challenging, and that is some feedback we've gotten before, and so something we can work on in the future. So a question from BJ Fregley, can prescribed joint motions be read in from a file in OpenSim 4.0 rather than just hard-coded in the OpenSim model file as in 3.3?
No, we haven't made that capability yet.
Yeah, so that's another one. Thanks for the feedback and the push, but that's something that have to come in 4.1 or 4.2. So a question from Ryan Kim. I guess either Tom or AJ could take this one. Could you please explain how to change or modify the muscle model? So that's a big one. I think it depends partly on what you're trying to do. So
I think they might mean like, how do you change the muscle model type? So if you were like using a Thalen muscle and you want to switch to a Matlab muscle, I think we have or are working on a script to help you to do that. Not all the muscle models are compatible. They don't have the same parameter set. So it's not just a simple switch. So if you, for example, in your XML file just changed all the tags, you would get some of the default parameter values for a muscle model that you switched to that you didn't specify in the old model, and then parameters in the old model that aren't defined in the new are just ignored. So it's not a perfect mapping between muscle models, but you can do that as a first pass, and then change the properties in the GUI.
I guess not a question, but a response. So James Dunn, one of the OpenSim development team, he's been working on a lot of utilities to help ease the process of getting the C3D data in and then getting it to work with the other tools in OpenSim. And so there's those utilities are available as part of the OpenSim distribution that you download. Where are those files located again, Iman? In code, resources? Yeah, if you look in your resources, like where your models live, I believe is where it's located. And you'll find some Matlab utilities to help read in C3 data and write out TRC marker data files and MOT force files. Let's see. Oh, so Ryan Kim chimed in again with some more clarification about his question. So is it possible to change a hill type muscle model to a different muscle model?
All our muscle models are hill type, so we don't have any other. You're welcome. I mean, the only other way would be to write your own muscle model,
right,
which is a bit easier to do now than before.
So you'd have to be a C++ developer to do that. Okay, so maybe we will take. We're already over. We're past 11:30. I appreciate all the great questions that are coming in. Let's see if there are any other quick one. One more quick one. Could I ask about Simulink? I don't think I. So another question from Naji Alabeji. Are there any functionalities that allow for the use of OpenSim models in Matlab Simulink? I'm going to take that one, EJ.
It's been a while since I used Matlab and Simulink, but yes, so all the API calls you can wrap in M functions and then expose them as blocks in Simulink. There is also the potential to compile down the C++ code for performance into MEX blocks and then load them into. That was something we had done a long time ago, led by Jeff Reinbold. But currently, it shouldn't be necessary to do that. You should be able to access the pretty high-level API calls and directly in your own M functions.
Okay. So since we're already past 11:30, I think we'll go ahead and wrap up the webinar. If we didn't get to your question, we'll compile all the questions that were asked and make sure we either answered them verbally or can post questions posted in our FAQ on the OpenSim documentation to make sure all those questions get answered. And as always, we encourage you to ask us questions on the OpenSim forum as well. So to wrap up, if you would, yes, so thank you, Tom, for being online to help us answer questions. Thanks to AJ and Iman for helping run the demo and the webinar, and thanks to Joy, who's helped us moderate. You can learn more about OpenSim on our website. We'll follow up with an email with more information about all the things that we talked about during the webinar. And we also encourage you to fill out the survey that's going to appear after the webinar ends so you can tell us what kind of topics you're interested in hearing about in future webinars. So thank you to everyone, and we hope. Oh, AJ wanted to.
I noticed that there were a lot of questions still unanswered. So please repost them on the forum so that they don't go unanswered. So
well, we typically in the past we've also compiled a list of all the questions associated with the webinar and shared those with everybody too.
Perfect.
Yeah. So. Yeah, so thank you again to everyone and hope to see you soon on the forum or in future webinars as well.